Okay, welcome to the DDPS seminar, everyone. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences. Therefore, no classified discussion is allowed, so please watch out. Finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Santi Adavani, who is a CTO and co-founder of RocketML. As CTO, Santi drives the technology roadmap that includes the design and development of scientific machine learning solutions. Prior to RocketML, Santi worked as a senior data scientist and AI product manager at Intel, where he led the development of AI systems for automated data management for yield enhancement. He received a Ph.D. from the University of Pennsylvania, where he developed fast algorithms to solve partial differential equation constraint optimization problems on supercomputers with applications in electro-cardiology. Today, Santi will talk about industrial-grade scientific machine learning challenges and opportunities, which is a very interesting topic. Please enjoy and expect a wonderful talk. Now, without further ado, let me pass the baton to Santi by asking one random question. As usual, today's question is, what is your favorite things to do other than your job role as a CTO?
Thanks for inviting me. So yeah, my favorite thing, I play volleyball in my free time, and if the weather is good, I go hiking. Pacific Northwest has beautiful trails around, so that's the other thing I do.
Nice, nice. Well, with 100-degree, I guess you're not
staying indoors.
Yeah, okay. All right, stage is yours.
Thank you. Okay. Hello, everyone. It's great to be here. So today I'll talk about industrial grade scientific machine learning and challenges and opportunities. So before I go in, I would like to thank all my collaborators from RocketML, Iowa State University, and NYU. And with so the challenges and opportunities I'm going to talk about today are about how do we take scientific machine learning that is more in the academic setting today, and how do we make it ubiquitous? How do we make it so popular as machine learning in general? And how do we make it accessible to a lot more people, a lot more organizations, so that we see the real value of SciML going into industry? So for those of you who have not heard about this before, so this is my talk outline. I talk about introduction, tell you what SciML is, and motivate the problem I'm looking at a little more. I'll talk about challenges and opportunities, and in specific, I'll discuss about ambiguity, scalability, and deployability problems, and I summarize my talk. So that's the outline. So SciML is scientific machine learning for short, and this is the definition from Department of Energy in 2019. So the way it's defined is it's a core component of AI that can be trained on scientific data, right? So that's the 10,000-foot level definition. And in order to simplify it, the way we look at it is at the intersection of laws of physics, science, and machine learning. And that is the intersection that we are most interested in, and we are talking about SciML. So from this 10,000-foot level definition, if you want to kind of bring it down and look at SciML through the lens of data and the lens of amount of information used, on one end of the spectrum, we have scientific computing, right? This is the traditional way of solving physics problems or chemistry or any science problems, right, for that matter. We have the formulation of the problem, be it PDE, ODE, or any other way of defining in a scientific manner. And we use traditional methods, finite elements, finite differences, molecular dynamics. finite volumes, so on and so forth, and we solve a given physics problem, right, using traditional methods. And on the other end, we have large-scale machine learning world that is exploding. That is, you have a lot of data coming from either simulations, a lot of data coming from sensors, and we are using all the data where the physics is implicit and building these machine learning models, large-scale machine learning models to explain the physics or to embed the physics in a model. And there's a lot happening in between, right? So that is, you're using the best learning from scientific computing, and you're also using the learnings from machine learning. And this coupled region is what we can term as scientific machine learning, where you're using data as well as the physics from either explicitly or implicitly. And there is a lot of work going on in this space, be it solving PDEs using neural networks, be it solving inverse problems, and a lot of methods being developed in the community, which has significant implications for simulations, control, design, and inverse problems. So the value of scientific machine learning is very well understood. So that is, when you go talk to somebody in the industry and explain the value of SciML, it's very clear. That is, we are going to speed up time to solution. So the time to solution for a given problem can be accelerated by orders of magnitude is a value proposition that everyone understands. And that's a baseline that we can think of when we think of SciML. And here I'm giving you two examples that were published from our group. The first one is a fluid flow problem where a traditional method would take around 400 seconds for simulation, and using a SciML model, it would take around 10 seconds. Right? So when I'm talking about the SciML solution, I'm primarily talking about the inference side of things. That is, I've already built a model, and I'm using that model to do inference. Same thing with heat transfer. So if you have a steady state heat transfer problem, you can solve the problem using a traditional method, which would take a lot of time. In this case, I'm talking about a 512 cube problem with millions of pixels or voxels. And when I try to solve the same using ML, it would take around 20 seconds. So the value proposition for using SciML is fairly clear, and we've been demonstrating that. But the challenge is, how do we take this from lab to bedside, right? So how do we make it industrial grade for applications that have high societal impact and have very low margin of error and have to be robust and fault tolerant? So how do we go from having this academic discussions and having all these publications which are doing really amazing work, and take it from there to actually being used in, say, designing heat exchangers or designing drugs for or designing different implants for in the medical industry, right? So what are these challenges to make SciML more ubiquitous, and how do you make it accessible to industry and industry researchers is the challenge that I'm going to discuss today. The first challenge that we run into is ambiguity, right? So that is, when we're talking about traditional solvers, the terminology that we use is fairly clear. That is, you have certain control parameters, be it boundary conditions, initial conditions, material properties, and you want to solve a PDE. So I'm going to discuss most of the topics in the context of PDEs because that's one of the major work that's happening. And within that context, the terminology is control parameters, you have a solver, and you are predicting certain state variables, right? So for example, in the case of boson problem, a steady state heat equation or conductivity or a lot of applications that can be modeled using this elliptic equation. One of the use cases is you're changing the diffusivity or the input material property, in this case, nu, and you're trying to predict a solution, which is the output of this equation using a solver. So the input-output mechanisms of a traditional solver is fairly well understood, and the terminology around solving a PDE is also very well understood. But when we talk about translating this problem into a deep learning problem, where there is innovation that is needed across all stages, things start becoming a little more ambiguous and vague for communication purposes. And this is one barrier we see for a lot more people to start using SciML and trying to make best use of all the innovations that are happening. Right? So just to make this a little more clear, when we are going from a traditional problem to a deep learning problem, now we need to think about scientific machine learning in the context of a neural network. And that is, what is the input data? How are we defining the input data? How do we represent that data? For example, is it points? Is it voxels? How are we representing this data? And what are the network architectures used? Right? For example, in some cases, you want to use a multi-layer perceptron. In some cases, you want to use CNNs, et cetera, et cetera. And there's a lot of innovation happening even within the network architectures, and you want to define the loss functions, right? So, and there's a lot happening within the loss function space. So a few examples within that is when we talk about network architectures, these are some of the work that we do internally. We try to classify these as point-wise architectures and full field architectures, right? So when we talk about point-wise architectures, the main problem we are looking at is how do we map a single point to a single point, right? So what that means is you have material properties or certain control parameters where you're training the network using a single point in the mesh or a single point in the domain, and you're predicting the output. So it has its own pros and cons. And from a industry point of view, this has implications. That is, you may be able to train very fast, but inference would require you to sample at a lot more points. And also the other implications are you're solving one instance of the PDE, but you may have to enforce these boundary conditions explicitly in your loss function. So that those become some challenges. And obviously there are a lot of advantages of using point-wise architectures. And when it comes to full field architectures, the idea is you can actually pass in a full field as your input and get a full field as your output. That is, the input properties you're passing in are an entire mesh or an entire voxel grid in this case, and the output is a solution of that. So in this case, the pros are you can enforce your boundary conditions exactly, but training becomes expensive. But inference could be much faster because you already trained a network enough with enough samples. And you can also solve a parametric set of PDEs and not just a single PDE to be used this for other use cases. And when it comes to loss functions, this loss function that we work on internally is, can we define the loss function without using any simulation data, right? So for example, when we define a neural network architecture and try to predict an output, you can either compare that output with an existing simulation data, right? That way you can use the traditional loss functions to simulate it. Or you could use the respective PDE and use that as a residual to train your network. So in this case, one of the things we did was we write the solution in terms of the basis functions and use Galericon method to multiply the test function with the solution and apply an integral on it to define a loss function. So what this allows us to do is it allows us to actually impose the boundary conditions exactly, and also use the literature from finite element methods to describe convergence criteria, describe error bounds, and get good results. So there's a lot of work going on in this space, but when we actually have to communicate this with external parties and try to say, hey, how do we go about using this? There are a lot of questions on what is the method does, what are the problems we are solving, and how does it compare with existing solutions. So one opportunity we see here is, and also this is something that we can work as a community, is establishing a certain ontology around scientific machine learning. And here again, I may be talking about a specific subset of the problems that we encounter at RocketML, that is within the partial differential equation space. But SciML itself is a much broader umbrella with uncertainty quantification problems, a lot of problems that we are not 100% aware of, and that's where I think we can also work with the community, in this case, the audience here, to grow this language that we are speaking, right? So the language that we speak, especially in the PDE space, is, hey, what is the input data? What are you trying to use as input for your neural network? And in this case, the cases we work with are material properties, boundary conditions, geometry, and so on and so forth. And if you look at the counterpart in the machine learning world, you can think of these as like, there the language is fairly clear. You're talking about either NLP problems or image problems or tabular data. So the language there is fairly clear, and we need within the SciML community our own way of describing the problem we are solving. The second thing is data representation, which is points, voxels, graphs. This is one way of representing the data. And each of them have implications in terms of how we solve the problem, right? Because points require a different architecture, voxels require a different architecture, graphs require different architectures. And how do we represent the network, right? So once we have the data representation and what we're solving, what is the network representation? Is it MLP? Is it CNNs? Is it graphs? And there is a lot of innovation happening within each of these network representation, and Fourier neural operator is one of the popular ones. And how do we make it clear for somebody looking at this as an innovation? And last but not least, the loss function itself, right? So that is, you have data-driven methods where you need simulation data, and you have data-free methods which take advantage of the PDE formulation or the physics information to describe your losses, right? So, and within that, you can have point-wise, full field, FEM, FDM, and so on and so forth. So this is one challenge. I think we have a communication challenge and ontology challenge that we can solve by trying to come up with certain criteria. And the other thing is benchmarks. So we need these benchmarks that are fairly well established in the ML community, but we need these in the SciML community, which is, what are the problems we are solving, right? So are you solving an ODE, PDE, steady state, or like, definitely this list is not exhaustive. What are the problems you're solving? And then the data sets, right? So for example, can we have this industry standard data sets for these different problems? Can we have these geometries, boundary conditions, initial conditions that industry at scale is very interested in to solve, so that any innovation that is happening in this space can be easily taken by for the real world problems. The third one is accuracy performance. It's like, how does this new method or this new technology in terms of data representation or neural network or loss function, how does it work, and what is the accuracy performance for that new method is another thing we can work on. And the last two are training performance and inference performance. That is, what does it take to train these models, and what does it take to infer, right? So these are some of the benchmarks that we can put together and encourage the community to chip in, to engage in this conversation, to improve these benchmarks, and also come up with new ways of describing the work. The second challenge, which we focus fairly on, is the scalability aspects of it. So most of the challenges that we see for industry adoption is also about the scale. Solving in a 2D problem in a small setting versus solving it at scale is a whole different challenge. So I'll give you a very detailed example here, and the way we solved it at RocketML. and that can trigger some conversation. So the problem we were looking at here was solving an elliptic problem. And in this case, we were looking at training a neural network where the input is in diffusivity, in this case, the value of nu in 3D. And the output of the solution is what we want to predict using this neural network. And it has Dirichlet boundary conditions on both sides and Neumann on one side, and there is no forcing function. So in order to train this network, especially when you're working with, say, using a network like 3D-UNet in middle, the challenges we run into are training these nets on GPUs is expensive. Right? So GPUs have relatively small memory, and when we have large image volumes, because when we're talking about scientific computing problems, the grid resolution still matters. Right? So you still need to have finer grid to resolve the physics. And when you have large image volumes, and even for a fixed network size, the peak memory that you need on a GPU would exceed. Right? So, for example, once we hit a 128 cube, we can no longer use certain Teslas. And once we hit more than 128 cube, we cannot use V100. And even with the latest ones like A100, there is always an upper limit in terms of how far you can go. And the only way around this is scale out. Right? So we need to train on multiple nodes, multiple GPUs, and using a HPC cluster. And once you go to the scale, it's no longer just distributed computing problem. That is, how do we use these GPUs for optimal memory consumption, and how do you use the CPUs? It also becomes a matter of how do we take advantage of the parallel file system, because you may want to do checkpointing in between and use the file system for existing data and so on and so forth. And how do you manage your Ethernet bandwidth to communicate between the nodes, etc., etc. So it becomes a distributed computing problem to solve SciML at scale. So we tried that, right? So we basically said, okay, the simplest thing we can do is scale it out. So let's use more GPUs and throw more at the problem to see if we can solve a problem, solve this 3D training problem. And what we concluded was, yeah, we put in more machines, and we were able to train. It took us around 34 hours to train this on 8 GPUs, but just throwing more GPUs at the problem is too slow, and it's not sustainable. So the challenge we went was, like, can we come up with some kind of algorithmic innovations, right? So we can always throw more compute to solve a problem, but that is not sustainable. How do we use algorithmic innovations? So this is where some of the ideas from existing solvers, right, from the scientific computing world, can potentially be used in scientific machine learning also. So the methodology we went after, and this has been published in last year's supercomputing paper, is using this multi-grid approach to train networks using hierarchy of mesh sizes. Right? So for example, instead of training this network at the finest resolution, can we train the network at a fine resolution, but don't train completely? Use the network weights to train the coarser grid network, and continue to train that until a point where you can still resolve physics, but it's not too small. And use those network weights to iteratively update your solution at other grids. Right? And bringing some ideas from the scientific computing world and applying it here has given us some benefits in terms of training. So in this case, for a little more detail here, we started off with a depth 4 unit. So what I mean by depth 4 unit is I have 4 layers in the downstream of the unit, and 4 on the top, including the bottleneck layer. And the first thing we do is basically take in a coarser resolution data set and train that coarser resolution data set on this 3D unit. So once we train this, and in this case, we don't have to train this for the entire until convergence, we can actually stop it in between. And once you have that, we actually build a new network, right? So what I mean by a new network is we take in the depth 4 unit and plug it in as a part of the network that is of a bigger size, right? And once you have this, you can transfer these weights to this underlying network and do this transfer learning, right? So when I'm talking about transfer learning here, I'm talking about going from one node, right? So when I say one node here, it's basically going from one level to the next level. Okay. So once you figure out this this network transfer in terms of weights and experiment with different combinations of these V cycle, W cycle, and F cycle, and so on and so forth, you can come up with the best combination of accuracy and speed up and use it for training, right? Because once we start training these models, they can become pretty expensive in terms of both compute cost as well as runtime. Okay. So what I'm presenting here is basically the results from that work, right? So we still left the problem with 8 GPUs. So for example, in this case, we trained the baseline with 8 NVIDIA GPUs on Azure. And for training a 256 cube resolution problem, so in this case, I have a lot of data which we basically generated synthetically and used it for training, and that took around 2000 minutes, right? So the plot you see here is basically training a 256 cube problem up to convergence, right? So I'm not showing the entire x-axis here, but to reach certain loss value, it took around 2000 minutes. And the same problem to basically train using multigrid, that is, we started off with a 32 cube problem, trained it to a certain number of epochs to see how far we can get the loss value, and then use that network for 64 cube and iteratively went down the or increase the resolution, right? So what we are presenting here is basically what does that mean, right? So for example, when you're using multigrid, using 32, 64, 128, 256, for smaller grid sizes, because the network is also smaller, you can train faster. Right? So it takes around 10 minutes to train the first branch of this network. And then as you go for larger sizes, in this case 64, it takes 20, and so on and so forth. But the cumulative time it takes overall to train this is just around 150 minutes compared to doing this standalone. So standalone basically trains, takes a very long time. And you can not only see the value of that, and obviously in terms of the time, but also in terms of cost. So the idea of doing things at scale also need to become first-class citizens, in the sense, in addition to training or building these models at small scale, doing it large scale is important. And here, if any of the audience working on any small scale problems and see potential for this at large scale, we are happy to collaborate with you and bring in RocketML's expertise in HPC and deep learning to train these problems faster. And these problems can also be solved on CPU clusters sometimes, right? For example, if you want to solve this at 512 cube resolution, so instead of solving at 256, and you want to scale it out to 512, and this is just doing distributed data parallel deep learning, even that won't fit into it won't fit in GPU memory, and you can use CPUs to train these. So in this case, what we did was, obviously doing it at 512 cube resolution on CPUs, it's not feasible. It takes forever to do that. But you could do this mix and match, right? So that is, you can train your networks all the way to 256 cube on on these GPU clusters, and take those information and take it from GPUs and do few iterations on CPUs. Okay, so that way you basically can take advantage of your CPU memory, which is also much larger than the GPU memory, and do not have the implications of slowness on CPUs because they're not built for this kind of deep learning training cycles. And that gives best of both worlds, right? So you can flip from one to the other. And what we think is, instead of investing in more complicated uh, distributed algorithms that may not scale very well, we could come up with this kind of algorithmic innovations that can help training faster, but still using the existing infrastructure without giving up on the scalability aspects of it, right? That is, as you increase the number of machines, you want to reduce your time to solution. Okay. So this is basically the other the challenge. That is, scalability is one challenge, and we have some ways to solve them. The third one is deployability. So this is a problem in machine learning in general, and it is a little more acute, I think, within the SciML community. Is there is a lot of ecosystem built in, and there is a lot of solved solutions out there that have been solved for a long time, and there are existing software. So any new system has to work alongside with the existing tools, right? So it's ideal scenario, uh, but the main intent there is something already exists. Either a new solution works along with it, and if you want to replace it, that becomes a fairly big challenge, especially given an existing solution might be working very well for that matter. Right? So with that challenge, and you bring in these challenges with machine learning itself, right? So machine learning has too many wheels. So um, what I'm showing here is applicable even for any general purpose machine learning, let alone scientific machine learning. There are a lot of things happening when you go from prototyping to production, right? So what I mean by that is, you're starting off with an idea. We are saying, okay, let me try to solve this scientific computing problem using machine learning. So you start building a hypothesis, and you start identifying your data sets, and you do some kind of exploratory data analysis and start building a model. And within building a model, there are going to be a lot of cycles. That is, you have to work with your refining the data. You need to work with defining your network architectures, try to apply new methods that are coming in the community, and come up with a model that is reasonably that is reasonable, right? That works well enough to say, okay, let me take this and go to production. But how does that model integrate into an existing system, right? So how do my users downstream who are familiar with using these existing solvers, can they use my new solver that is based on machine learning? Okay. So there are these operational challenges which basically makes it a problem for anybody doing a prototyping on ML to take it to production, right? So actually, when I say take it to production, how to make people actually use these models that are built at scale, and that might be working fairly well. So a few solvers. So the way we are addressing this is basically build these SciML solvers that are easy to consume, right? So can we make any of these solvers consumable? Like, can we give them something where you can bring in a geometry or bring in physics models and try to use these inputs, right? And whatever the input data that we are talking about, and for different domains, these inputs might be different. And can we build these SciML solvers that take in these inputs that the users are familiar with, and you can actually build a solution or solve the problem on the fly and give them a solution, right? So we need to think about a different way of integrating these latest innovations within the SciML community and trying to make it easy for others to consume. Are there any SciML solvers that are readily consumable that we can put out there? And if you're working on any specific problems and you want to package them as solvers, we are happy to chat with you offline. The second problem is, let's say we want to have a technology that where we are not providing the solvers, but we want the researchers in an industry or researchers in an organization to build these models, right? So in that case, they will need an entire platform that can not only work with respect to model discovery. So this is the first box here, is where a SciML researcher would work on figuring out, okay, what is my problem? What is the data I need to work with? What is my scientific problem that I need to formulate as an ML problem, and use one kind of compute, right? So in this case, CPUs, GPUs to generate the data as well as train and build a model. And then once the model is built, it is non-trivial to deploy it. Let's say we deploy it. That model is only as good as the data that it saw, right? So any ML model, doesn't matter whether it is scientific or otherwise, requires some kind of monitoring, some kind of retraining, some kind of way to say, okay, this is no longer working well for the problem at hand, but how do we improve it? Okay, and what are the retraining triggers that we need to look at? Are all the unknowns at this time, and some kind of a platform to enable this entire pipeline is something that's interesting. And this is another thing that we work on, which is how do we bring these scientific computing world and the machine learning world together, so that whoever is trying to build these models get best of both worlds. That is, they can check whether their ML model is working as well as the traditional solvers, and not only that, it makes it easy for them to deploy, so that the end users within the industry can actually consume and get the best value out of all the innovations that are happening. Okay. So with that, 40 minutes in, so SciML, to summarize, I'm kind of wrapping up talk, and SciML is transforming simulation sciences and has compelling value proposition for the industry. We can demonstrate that it is energy efficient, obviously, once the model is built, and we can reduce the time to solution. That is one of the bigger value propositions for that resonates very well. And it has relatively lower memory footprint, because once you train, they have a model, they can take advantage of it. And the opportunities to accelerate this transition from traditional to SciML, a lot of opportunities here that the community can work alongside industry, that is establishing an ontology and establishing certain benchmarks. Bringing in HPC scalable solutions, because scientific computing is a HPC heavy domain, and bringing in HPC scalable solutions is very attractive. And tuned platforms towards more of a scientific machine learning use cases, so that we can deploy the solutions, make it real world, and have real world impact fairly quickly, and make this overall space more accessible and ubiquitous for more people coming into this industry. Okay. So with that, I thank you for your time. And I'm happy to take any questions.
Thank you so much for the wonderful talk. I really enjoyed it, Santi. Very new perspective from the CTO who works in the industry on the scientific machine learning. Okay, let's have a Q&A session. Maybe you can keep the slide codes some of the question is specific to specific slide. So if you can share that again, that would be wonderful. All right, and yeah, so there are in chat room.
Young Sue, this is Pat. Why don't we talk with start with the technical questions, and if there's time, we can come back to the terminological issues.
Yeah. So that's what I was about to suggest. So that okay, Pat. Thank you so much for stepping up on that. Okay, so sounds good. Let's do the technical question. If you have any questions, then please do so. I do see one technical question from Georges. He asked, how do technologies like unified shared memory perform for avoiding the limited GPU memory problem? I guess that's related to your multi-grid approach to overcome the memory issue of the training the neural net.
Yeah, I mean, so the way we think about it is, yes, so there is a lot of innovation happening in these spaces, right? That is, there could be more memory available using, by the way, I'm not familiar with that specific technology, but there is always more memory needed to train these networks because either the network is getting bigger or the problem resolution is getting bigger. So we will always hit a limit in terms of how much you can use. It's a typical HPC problem. And if there is a new technology, I'd say this approach still is applicable for using more memory and maybe solve bigger problems.
Okay, related to that, how diverse, the different problem have you tried this multi-grid training to, Santi? I mean, the examples you have shown, obviously, that's one particular problem.
Yes, yeah. So we have tried this for this Poisson problem, and we also tried this for a fluid flow problem also. So, which is basically used it for Burgers equation, where the input is initial conditions and the output is the full field. Yeah. In that case, the problem was no longer just unit. We had both fully connected layers as well as convolution layers, right? So in that case, how to do the transfer learning becomes kind of tricky because it's not fully convolutional like unit. So we have tried this in other cases also, and we have seen similar results. That is, by doing this transfer learning using multi-grid, we saw speed up in training times, and almost at the same scale. Like we could show 5 to 10x speed up in training once you start using a lower resolution train network on higher resolution. We could show things speed up.
Okay, sounds good. Dan White asked, we can put error bars on FEM simulations, although we don't do it every day. Can you put error bars on your ML models? This is essential for adoptions by real engineers.
I think for absolutely. So for error bars and ML models would be, how do they compare with FEM? That would be the right error bars. And that's where we need certain benchmarks saying, okay, if there's an ML model for this problem, this is the best we see in FEM, and how does it compare with that FEM simulation? So in my mind, the baseline would still be a traditional solver, and any ML model error bar would have to be relative to that, right? And I completely agree. We need error bars on ML models, and that will help in adoption by real engineers.
All right.
Yeah.
Okay, so there's George's. He has a comment on the about the memory issue. So he said unified shared memory is already available in NVIDIA GPUs since CUDA 6. He shared the link, and it works like a page swapping across this CPU GPU memory boundary. So I guess you want to check that out.
Yeah, thank you very much.
By the way, do you have access to the chat room?
I can see the chat window here.
Oh, awesome. Okay. Well, then you will have a link.
Right.
Okay, sounds good. Wait, any other question from audiences? About the continuous integrations,
Yeah.
I mean, that's the big challenge, you know, we have to resolve. I totally agree with that. And the main, probably, the reason why that's a challenge is the reproducibility of the neural network, as well. So if you can elaborate more on that aspect, that would be wonderful.
Yeah, so when it comes to deployability, there are challenges coming from the machine learning world. I mean, even within the traditional ML world, this deployability is a huge problem, and a lot of problems still stay in the prototype phase and never reach production. That's because the language gap. Right? So, for example, when it comes to ML, what does deployment actually means? Is it an application or is it an API that somebody can integrate? And how does it work is one problem. And you're absolutely right. So that is, when it comes to the SciML related problems, it is the matter of both reproducibility, that is, given a new input parameter. Right? Let's say I've trained a network with a whole bunch of material properties, and I know that model should work very well for a new material property. Then can I rely on that new network to give me a solution is a matter of the data in which it was trained on, right? So what is the data distribution that it was initially trained on is going to be the main question, because any new input that you give should be in that distribution for giving the right solution, right? That is number one. That is your model going to drift from the trained model? And if so, we need to let the user know that, hey, this model is no longer doing very well, and go back to your traditional solver for this case, right? So there should be this kind of transparency in terms of this model performance. That is, we need to be very clear to say, okay, these models work for these cases, and we are going to give you some error bounds on how they work. And if this error bound is not suitable for you, go for another method, right? So we see these ML models to be as another tool in the toolkit for the engineers who are designing these things, and not the only tool. That way, they can compare and contrast. They have the same error bounds and error mechanism that they can evaluate any other new method, right? And use along with their existing tools. So a lot of different dimensions that we can think through when it comes to deployability. Well, errors is definitely one big thing.
Okay, sounds good. Okay, there's not a question, but the comment from Rob. He said it's not too difficult to put a PyTorch or Torch script model inside a C++ code.
No, it's not too difficult to put a.
Well, Rob, he has worked on it in the past. I mean, you said it's not too difficult. I don't know. It's a somewhat.
Yeah, it becomes, if you want to do, yeah, we can chat about it offline. Right? If you want to do training, it becomes non-trivial. If you want to do inferencing, going from PyTorch to C++ is fine. It depends on how we're going from one to the other. And if the question is it, can this solve the deployment problem? I do not. I mean, a lot of systems are already set up, right? So going into a C++ code, maybe a starting point might not solve the 100% of the integration problems. So, so yeah, that's my comment for that question, if there was any.
All right, sounds good. Is there any other questions? Any other technical questions? Then I would like to give a, the Pat the chance of.
Thank you.
Yeah.
And thank
the
you
panelists.
for the talk. And I just want to be clear. I have no issues with the technical content of your talk. I mean, I'm happy to see you making progress on these issues, and they're all important problems. The points I raised early in your talk were about terminology and the scoping of the problem. You seem to be talking about this as though it was for physics rather than other fields of science, you seem to be assuming that we had to be working with large data sets rather than small data sets, even though there's been lots of work in machine learning on small data sets. And you seem to be focusing on neural nets, even though neural nets are only one of the many paradigms in machine learning. And so I just wanted to encourage you to use language that was more inclusive, that acknowledged that machine learning is a broad field, that it can be applied to many different sciences, not just physics, and also to reconsider the term scientific machine learning, because it suggests that it's broader than what you seem to mean. That is, I do not take it that you are working on discovering new scientific laws from actual data, but rather making existing models more efficient. That's fine. That's an important problem. But scientific machine learning suggests that it covers everything, and we have other terms for fields like computational scientific discovery that I think are more narrow and more focused. So that's just my suggestions.
Absolutely. So Pat, you actually hit on it. That's one of the challenges that I'm talking about as the first point. We being in the community, we have at least some overlap. There is a problem with terminology between what we work on and what you work on. And I think that's where I want to kind of make this point that even with people who are working in this space, we are unable to agree on terminology.
I'm sure.
Right. And imagine, so when we go talk to folks, they have no idea, right? When I say they have no idea, people are very smart. But if we are not able to agree on a terminology, how are we going to get more people into this, right? How are we going to make this more ubiquitous? I think there is an opportunity here. That's what I'm trying to bring in, right? We have an opportunity to create certain terminology that where when we're talking about problems, we're talking about specific problems that the other person knows, okay, they're working on this. And I'm happy to chat with you offline because I think there's a problem that needs to be addressed today.
Sure. Part of where I'm coming from is that I've been working on using AI and machine learning methods to discover scientific laws for over 40 years. Okay, and it's recently become a popular topic again, and I'm pleased that people are rediscovering some of our old work. But I remember working on this for a long time and saying, well, what's this field called computational science? Which was because I thought I was doing computational science, but no, computational science was narrowly defined to be PDE models and getting them to run efficiently on high performance computers. And I felt locked out because the computation, basically people who were doing computational PDEs had taken this term. It sounded a very broad term. It actually had a very narrow meaning. And so I just encourage people to use terms that reflect the breadth of what they're focusing on and not try and own the territory. You see the same kind of thing all over AI. For example, graphical models. There are a lot of graphical models that don't count as graphical models, and I think that's unfair.
Right. And I resonate with that, and maybe I can chat with you offline. And this is exactly one thing I think we can solve as a community. At least I think have motivated folks here, and want to bring that thing into the mainstream so that I'm like, for example, myself, I'm not familiar with your work, but we could bring that as saying, hey, let's figure the terminology first and make whatever work fit into this. And if you want to add more, we can add, right? So I think there's an opportunity for us to work here.
I'll be happy to talk with you offline. Thank you for being so open to this.
Thanks, Pat.
Wonderful. Well, that was very productive. And although, the community we gathered in this webinar series it's not representing all the communities in scientific computing or scientific machine learning, but it's I guess it's definitely a starting point talking about the clearing the terminology here.
Absolutely.
All right. Any other questions or any other things you want to discuss before we add John? If not, let's thank our speaker Santi for the wonderful talk, and and thank you everyone to join the DDPS seminar. Next one is actually the next week, so after a short period of time, we'll see you again. Okay, thank you everyone. Thank you, Santi.
Thanks, everyone. Thanks, Young. Thanks for inviting.